All right, so today we're going to do a deep dive into ImageNet classification with deep convolutional neural networks.
Yeah,
It's
a mouthful.
it is a mouthful, but this paper kind of set out to teach a computer to see, and the results were absolutely revolutionary. You sent this one in, so you're clearly as fascinated by this as I am.
Yeah, absolutely. It's a landmark paper for sure.
Yeah.
Alex Krasevsky, Ilya Sutskever, and Jeffrey Hinton, back in 2012,
Yeah.
they basically changed the game for computer vision.
They completely dominated the 2012 ImageNet competition.
They did.
What made their approach so different?
Well, I mean, their secret weapon was really this powerful combination of a massive data set, some, really clever algorithms, and some serious computing power.
Yeah.
And so ImageNet itself
Yeah.
is this incredible collection of over 15 million labeled images
Wow.
spanning a whopping 22,000 categories.
It's like a visual encyclopedia.
It is, yeah.
Yeah.
Think of it as a visual encyclopedia for training AI.
Yeah.
Did they use all 15 million for the competition?
So not all 15 million,
Okay.
but still a huge chunk. They focused on a subset of 1.2 million images
Got it.
and 1,000 categories for the competition.
That's still a mind-boggling amount of data.
It is, even that is a mind-boggling amount of data to work with.
So they had this visual encyclopedia, but how do they actually get the computer to see the images?
Right.
The paper mentions convolutional neural networks.
Yeah.
What are those?
So think of it like this.
Okay.
When you look at a picture, your brain doesn't just see a jumble of pixels, right?
No.
It identifies shapes, edges, and then puts it all together to recognize objects, right?
Right.
Convolutional neural networks, or CNNs,
Yeah.
they try to do the same thing.
Okay.
They're networks of interconnected neurons
Okay.
that are designed specifically to analyze visual data.
So it's like giving a computer a rudimentary version of a visual cortex.
Yeah, you can think of it that way.
That's wild.
Yeah. But if this is such a good approach, why wasn't everyone using it before?
Well, so training these networks,
Yeah.
especially on high-resolution images,
Yeah.
used to be incredibly computationally expensive.
Okay.
It wasn't really feasible
Yeah.
until relatively recently when, computing power kind of caught up.
So this paper is kind of where things started to change.
This is where things really started to change.
Okay.
They have the right model, the right data,
Yeah.
and finally the right computing power.
Yeah.
They use GPUs, those powerful graphics cards you usually find in gaming rigs,
Yeah.
to train their network.
Okay.
GPUs are perfect for the kind of parallel processing that deep learning needs.
Got it. But I read that they even had to get creative with the GPUs.
They did.
Didn't they run into a roadblock?
Yeah, so even with these powerful GPUs,
Yeah.
the network was too big to fit on a single one.
Wow.
So they split the processing across two GPUs,
Oh, wow.
essentially giving their network two brains to think with.
That's thinking outside the box.
It was a very clever workaround.
Yeah.
But, training this massive network still took a long time.
Yeah.
And so they looked for ways to speed things up.
Of course.
And that's where ReLUs come in, or rectified linear units.
ReLUs, tell me more.
Yeah.
How did those work?
So it's a type of activation function,
Okay.
which basically determines how a neuron responds to its input.
Got it.
So think of it as a switch
Okay.
that decides whether the neuron should fire or not.
Yeah.
And ReLUs make this decision-making process
Yeah.
much faster.
Okay. Than previous methods.
Yeah.
So they found a way to make the neurons think faster.
That's a good way to put it.
That seems pretty crucial for tackling such a massive data set.
It's absolutely critical.
Yeah.
The speed boost was critical.
Yeah.
It allowed them to experiment with much larger and more complex networks.
Okay.
And it paved the way for the even more powerful models that we see today.
Yeah.
But with a network that big,
Yeah.
I imagine they had encountered some issues with overfitting. Right.
Overfitting, that's when the model gets so good at recognizing the training data
Right.
that it struggles with new images.
Exactly. Precisely.
Okay.
And with 60 million parameters in their network,
Wow.
overfitting was a major challenge.
Yeah.
So to tackle this, they used a couple of clever techniques.
Okay.
One was data augmentation.
Data augmentation, did they just find more images?
Not exactly.
Okay.
They took the existing images
Okay.
and created variation
Okay.
by cropping them, flipping them, and adjusting the colors.
Ah, okay.
So it's like showing the network the same object
Yeah.
in different angles
Okay.
and in different lighting.
So it's like giving the network a more well-rounded education.
Exactly.
Showing it more examples without needing to actually collect more data.
Yeah.
That's ingenious.
It's a brilliant workaround. But it didn't completely solve the overfitting problem.
Okay.
And that's where their second technique came in.
Okay.
Dropout.
Dropout. Does that mean they got rid of some of the data?
No, it's been counterintuitive.
Okay.
During training, they randomly switched off some of the neurons.
Really?
Yeah, imagine making the network study harder
Okay.
by taking away its cheat sheet.
Interesting.
Seems strange, but it forces the remaining neurons to work harder and learn more robust features that generalize better to new images.
So it's like a boot camp for the neural network.
Yeah, exactly.
Making it tougher and more adaptable.
Like a buffer, yeah.
I love that analogy.
Yeah.
These techniques to combat overfitting sound pretty clever. Did they work?
They did. They worked really well.
Okay.
The results in this paper were groundbreaking.
Yeah.
Their model achieved a top 5 error rate of 17% on ImageNet.
So out of 100 images,
they
only misclassified 17.
Which was significantly better than anything that came before.
That's a huge leap forward.
Yeah, huge.
The paper also mentions qualitative examples. Things like the network recognizing objects even when they were off-center.
Yeah.
What did those examples reveal?
Well, I mean, those examples provided valuable insights into how the network was seeing.
Okay.
They showed that it wasn't just memorizing pixel patterns.
Okay.
It was learning to recognize higher-level features and concepts.
So it could actually understand something about the objects themselves.
It was, yeah.
Even when they weren't presented in the most straightforward way.
Exactly.
That's amazing.
Yeah.
It's like the network was developing its own visual intuition.
Yeah.
I remember reading that the depth of the network played a crucial role in its success. What did they mean by that?
So they discovered that adding more layers to the network, making it deeper, led to significant improvements in performance. Removing even a single layer caused a noticeable drop in accuracy.
So deeper networks equal better results.
It seems that way.
It sounds like they stumbled onto a pretty fundamental principle here.
They did.
Opened up a whole new avenue for research.
Yeah, absolutely they did.
What happened next?
Wow.
What were some of the key advancements that built on their work?
So one major trend was, you guessed it, going even deeper.
Of course.
Researchers started experimenting with networks with dozens, even hundreds of layers. Pushing the boundaries of what was possible.
There's hundreds of layers.
Yeah.
That's mind-boggling.
It is.
But wouldn't that make the training process even more computationally expensive?
It would.
How did they manage that?
So advancements in hardware and software were really critical.
Okay.
We've seen massive improvements in GPU performance.
Yeah.
And, new tools and techniques have made training these massive networks more efficient.
Got it.
It's been a fascinating coevolution.
Yeah.
Better hardware enables bigger networks.
Right.
Which in turn drives the development of even better hardware and so on.
It's like a technological arms race.
Oh, yes.
Pushing the limits of what's possible.
Yeah, exactly.
But amidst all this progress with hardware and algorithms, what about the ImageNet dataset itself?
Yeah.
Has it continued to be relevant?
It has, absolutely. ImageNet remains a benchmark dataset for image recognition.
Okay.
And researchers have continued to use it to train and evaluate their increasingly sophisticated models.
So they've been using the same dataset.
Pretty much, yeah.
But with much more powerful tools.
Yeah.
I'm guessing the error rates have continued to plummet?
You bet.
Okay.
The error rates on ImageNet have dropped dramatically in recent years.
Wow.
In fact, some models have even surpassed human performance on certain image recognition tasks.
Hold on.
Yeah.
Surpassing human performance?
Yeah.
Are we saying computers are now better at seeing than we are?
Well, it's not quite that simple.
Okay.
While some models can outperform humans on specific, well-defined tasks, that doesn't mean they have a better overall understanding of the visual world.
Okay, so...
Think of it as specialized expertise rather than general intelligence.
Okay.
These models are incredibly good at what they're trained to do.
Yeah.
But they can still be fooled by unexpected inputs or subtle variations in the data.
So there's still a gap
There
between how computers see and how humans see.
There is. Yeah.
There's more to vision than just recognizing objects.
Exactly. And that's where ongoing research into model interpretability and robustness comes in.
Okay.
Researchers are trying to understand how these models make decisions.
Yeah.
And how to make them more resilient to things like adversarial attacks.
Okay.
Where deliberately manipulated images can trick the model into misclassifying things.
That makes sense. I mean, we don't want self-driving cars being fooled by a sticker on a stop sign.
Right.
Or security systems misidentifying people.
Exactly.
So apart from deeper networks, better hardware, and research into making these models more reliable, what other advancements have there been in image recognition?
Well, another exciting area is the development of new architectures and techniques that go beyond traditional CNNs.
Okay.
We're seeing researchers explore things like attention mechanisms,
Okay.
capsule networks,
Okay.
and generative adversarial networks, or GANs.
Attention mechanisms, capsule networks, GANs.
Yeah.
It sounds like we're going even deeper into deep learning territory now.
Yeah, deeper and deeper.
But those all sound pretty intriguing.
They are.
Can you break them down for us?
Sure.
Let's start with attention mechanisms. What are they all about?
So think about how you look at an image.
Okay.
You don't process the entire scene at once, right?
Right.
Your eyes dart around, focusing on different areas of interest.
That's right. If I'm looking at a photo of a cat, I might focus on its face first.
Exactly.
Then maybe its paws and so on.
Uh-huh. Attention mechanisms aim to mimic that selective focus.
Okay.
They allow the model to pay more attention to certain parts of the input image while ignoring less relevant information.
So it's like giving the model a spotlight.
You got it.
To shine on the most important features.
Yeah.
That seems like a more efficient way to process information.
It is. It's much more efficient.
Yeah.
And this targeted focus can significantly improve the performance of image recognition models.
Okay.
Especially for tasks like object detection and image captioning.
Interesting.
By focusing on the relevant parts of the image.
Yeah.
The model is less likely to be distracted by irrelevant details.
It's like giving the model a dose of human-like focus.
Yeah.
Helping it to cut through the clutter.
That's a good way to put it.
Okay.
Makes a lot of sense.
Now, what about capsule networks?
Okay.
Those sound particularly interesting.
So capsule networks are a relatively new idea.
Okay.
But they've been generating a lot of buzz in the field.
Okay.
The basic idea is to represent objects as capsules.
Okay.
Which are groups of neurons.
Okay.
That encode information about an object's pose, position, and other properties.
So instead of just recognizing that there's a cat in the image, a capsule network might also be able to tell you the cat's orientation size.
Yeah.
And maybe even whether it's moving.
Exactly.
Okay.
Capsule networks aim to capture more than just the presence or absence of an object.
Yeah.
They try to represent a more holistic and contextual understanding of the scene.
That sounds incredibly powerful.
It is, yeah.
Are capsule networks living up to all the hype?
So they're still in the early stages of development.
Okay.
But they've shown promising results on certain tasks.
Okay.
There's a lot more research to be done.
Yeah.
But capsule networks have the potential to revolutionize image recognition.
Okay.
By providing a richer, more nuanced representation of visual data.
Okay, now how about we tackle GANs?
Right.
You mentioned those earlier, and I'm curious to learn more.
Sure.
GANs always sound a bit mysterious to me.
They are.
What are they all about?
So GANs, or generative adversarial networks, are a fascinating type of neural network. They consist of two networks that are pitted against each other.
Okay.
In a kind of adversarial game.
An adversarial game. Yeah. What do you mean by that?
So one network, called the generator, creates fake images.
Okay.
The other network, the discriminator, tries to tell the difference between real images from the training data and the fake images generated by the generator.
Okay, so it's like...
Imagine a digital art forger trying to create fake masterpieces.
Okay.
And an art expert trying to spot the fakes.
So it's like a constant back and forth?
It is.
With each network trying to outsmart the other?
Exactly. As the generator gets better at creating realistic images, the discriminator has to become more discerning.
Okay.
It's this constant push and pull that makes GANs so powerful.
They're essentially making each other better.
They are.
Like a training montage for AIs?
Yes.
That's pretty clever.
Yeah.
What can these dueling networks be used for?
They can do some pretty amazing things. Okay. They're used to generate incredibly realistic images.
Okay.
Which has applications in areas like art and design.
Okay.
But they're also used for tasks like image editing.
Okay.
Enhancing image resolution.
Got it.
And even in fields like drug discovery.
Wow, that's incredible.
It is, yeah.
GANs sound incredibly versatile.
They are, very much so.
So we've gone from these early breakthroughs with deep CNNs to even more sophisticated architectures, like attention mechanisms, capsule networks, and GANs.
Right.
It seems like image recognition has advanced at an unbelievable pace.
It really has.
It's a testament to the ingenuity and hard work of researchers all over the world.
It is.
Who are constantly pushing the boundaries of what's possible with AI.
Absolutely.
It's been an incredible journey.
It has.
Through the evolution of image recognition.
Yeah.
We started with that landmark paper that taught computers to see and explored all these amazing developments that have sprung from it.
Yeah.
Where do we go from here?
Well, that's the million-dollar question, right?
Yeah.
The field is constantly evolving.
Yeah.
And it's hard to predict exactly what the future holds.
Right.
But one thing's for sure.
Yeah.
The pace of innovation shows no signs of slowing down.
It's exciting.
Yeah.
And maybe a little bit daunting to think about all the possibilities.
Yeah.
They've already seen how image recognition has gone from,
right,
recognizing cats in pictures to powering self-driving cars and revolutionizing medical imaging. What's next?
So we can expect to see even more sophisticated models that can understand visual data on a deeper level, going beyond just identifying objects to inferring relationships, understanding context, and even predicting future events based on what they see.
So like a security camera that can not only detect a person, but also anticipate their actions.
Exactly.
Or a medical imaging system that can predict the likelihood of a disease developing based on subtle patterns.
That's right.
That's incredible.
It is, yeah.
But as these models become more powerful and integrated into our lives, are there any potential concerns we should be thinking about?
Well, that's a great point. As with any powerful technology, there are important considerations about responsible development and deployment. We need to ensure that these systems are reliable, unbiased, and used ethically.
So ensuring things like facial recognition systems are used fairly and not for discriminatory purposes. And making sure self-driving cars are safe and can handle unexpected situations.
Absolutely.
Those are definitely crucial aspects to consider as these technologies become more pervasive.
Yeah, I completely agree.
Yeah.
As researchers continue to push the boundaries of what's possible with image recognition, it's equally important to have open discussions about the ethical implications and societal impact of these advancements.
It's like we're giving computers a whole new way to see the world. Right.
And we need to make sure they're seeing it responsibly.
Very well said. Yeah. It's an ongoing conversation and one that needs to involve not just researchers and developers, but also policymakers, ethicists, and the public at large.
This has been a truly fascinating deep dive.
It has been.
Into the world of image recognition.
Yeah.
We've covered so much ground.
We have.
From the early breakthroughs with deep CNNs to the cutting edge of research with GANs and capsule networks. It's clear that this field is rapidly evolving.
It is.
With new possibilities emerging all the time.
Absolutely.
Well, I've learned a ton, and I'm sure our listeners have too.
Me too.
It's amazing to think that we've gone from teaching computers to recognize cats in pictures to exploring the potential of these technologies to transform fields like medicine, transportation, and even art.
It's remarkable.
It is remarkable.
And who knows what breakthroughs are just around the corner.
Yeah.
The future of image recognition is full of potential. Yeah.
And it's up to all of us to ensure that it's a future that benefits humanity as a whole.
That's a great note to end on.
Yeah.
Thanks again for joining us for this incredible deep dive.
My pleasure.
Until next time, keep exploring, keep learning, and keep looking ahead to the amazing possibilities that technology holds.